In traditional machine learning, evaluating a classifier is a straightforward binary process. The system has a single ground truth. The algorithm's objective is to draw a clean decision boundary that mathematically separates correct answers from incorrect ones, yielding a verifiable accuracy score. Generative models break this clean arithmetic. When a model produces open-ended text, images, or code, a single prompt explodes into countless valid responses. There is no single correct answer to check against. Instead of checking a single label, a generated response must satisfy multiple competing criteria at once. A summary can be highly fluent but factually inaccurate. A translation can be completely accurate but irrelevant or unsafe. This creates a structural constraint in generative engineering, known as the quality diversity tension. A deployed model must consistently produce high-quality responses, but it must also span the full range of valid, diverse outputs required by users. If an engineering team tunes a model exclusively to maximize average quality, it will inevitably default to producing the exact same safe, generic response every single time. This is mode collapse, a system that is perfectly reliable but entirely useless for open-ended tasks. Because fluency, safety, and diversity pull against each other, they cannot be collapsed into a single mathematical score. Standard accuracy metrics fail here. The field of generative AI has a severe measurement problem. This graph charts the engineering solution to the lack of ground truth, the evaluation ladder. The ladder illustrates the strict trade-off required to assess these models. At the bottom, automated metrics are incredibly cheap and fast to run, but they are crude proxies that are easily gamed. At the top, human evaluation is highly accurate, but prohibitively slow and expensive. Validating a generative model for a high-stakes deployment requires an engineering team to navigate this ladder rung by rung, applying different methods at different stages of development. Assessing a modern AI system is never a single calculation. It is a continuous process of triangulating reality using a portfolio of imperfect proxies. The first and lowest rung of the ladder relies on automated n-gram overlap metrics, such as BLEU and ROUGE. These are the cheapest evaluations available. N-gram metrics check for exact word sequences between a reference and the output. But because they only see exact text, they are blind to meaning. A perfect paraphrase is penalized, dropping the score to 0. To address this structural failure, engineers rely on the second rung, embedding similarity metrics, like BERT score. Instead of requiring exact word matches, embedding similarity maps outputs to mathematical vectors in a latent semantic space. It measures how closely the intent of the generated text matches the intent of the reference text. While embedding metrics capture intent far better, they are still just mathematical correlates of quality. They do not measure actual utility. This introduces Goodhart's law to machine learning. When a measure becomes a target, it ceases to be a good measure. If a research team optimizes a model directly against a similarity metric, the system will learn to produce verbose, heavily hedged responses. These outputs will artificially max out the scoring rubric while completely failing to answer the user's actual question. Relying solely on automated bottom-rung metrics guarantees the deployment of models optimized to gain the test rather than solve the problem. To compare architectures fairly, the field moves to the third rung, standardized benchmarks, like MMLU for knowledge and HumanEval for code. These are fixed, static test sets with known answers. They provide a normalized environment to evaluate disparate models against a common baseline. Benchmarks are most effective when tied to objective criteria. In HumanEval, a model generates a block of code, and that code is executed. It either passes the unit tests or it fails. There is no subjectivity to interpret. But static test sets face two major threats. The first is saturation. As models rapidly gain new capabilities, they cluster near perfect scores on existing exams. Once top-tier models all score above 90%, the benchmark loses its discriminative power. It can no longer rank the models or indicate true progress. The second, far more insidious threat to evaluation integrity is contamination. Modern large language models are built on massive training corpora, created by indiscriminately scraping petabytes of data from the open web. Because benchmarks are public, test questions inevitably get swept up in the web scrape. When the model is tested, it has already seen the exam. It is simply regurgitating memorized answers. Due to the ever-present threat of contamination, top-tier leaderboard scores are not empirical facts. They are claims that require deep algorithmic skepticism. Because human evaluators are expensive and automated metrics lack nuance, the industry has adopted the fourth rung, LLM-as-judge. This architecture uses a superior language model to evaluate the generation of a peer model. The judge AI scores the target AI against a strict criteria of accuracy, coherence, and safety. This allows engineers to process gigabyte-scale datasets with nuanced evaluation, operating at a fraction of the cost and latency of manual human labeling. But an AI judge brings inherent structural biases. The most prominent is verbosity bias, the tendency for the judge model to automatically equate length with quality, rewarding long answers regardless of their actual substance. Judge models also exhibit position bias, reliably favoring the first option presented to them, and self-preference, consistently assigning higher scores to outputs that match their own architectural style. Utilizing this method effectively requires strict engineering mitigations, randomizing the order of answers, enforcing hard length controls, and verifying against human labels. Even with mitigations, relying on AI to evaluate AI introduces the core conceptual hurdle of this methodology, the scalable oversight problem. The recursive paradox is that a judge model cannot reliably detect errors that it would make itself. It is blind to subtle reasoning flaws that align with its own internal limitations. LLM-as-judge successfully scales evaluation across massive datasets, but its recursive blind spots prevent it from serving as the final, trusted arbiter of a model's safety. To find absolute validation, the field must access the top rung of the ladder, direct human evaluation. Generative models are built to serve people. Despite being slow, expensive, and subject to fatigue, human judgment is the actual target that every automated proxy is attempting to approximate. The modern execution of this ground truth is the crowdsourced arena. Users submit a prompt and are presented with two anonymous AI responses side by side. The user simply votes on which is better. These arenas bypass automated proxies entirely. They aggregate millions of blind pairwise comparisons into an ELO-style ranking system, capturing real, unsimulated user preference at scale. Human arenas accurately map true utility, but their sheer cost and slow iteration speed mean they cannot be used to drive active daily engineering cycles. They are the final checkpoint, not the daily tool. For frontier models, deciding whether a system is ready for the public requires combining these rungs into a final deployment protocol, holistic evaluation. This radar chart plots performance across multiple dimensions, proving raw capability alone is insufficient. In production, these axes pull against each other. Tuning too hard for safety triggers over-refusal, capability collapses. This multidimensional reality shatters the illusion of a single score leaderboard. A complete engineering checklist requires all of the tools: fast n-gram metrics for daily iteration, verified benchmarks to establish baselines, LLM judges to scale the nuance, and human arenas to establish ground truth. In generative AI, our ability to measure naturally lags our ability to build. You can only safely deploy a system when you have rigorously triangulated its capabilities across multiple independent axes.